So once again, hi everyone, and welcome to Sweden VMUG. We are so happy and delighted to have you all on board. Today is a special day because we have Frank Denneman. We are honored to have him for the second time in Sweden VMUG, and we have two great sponsors. So thanks to them, NVIDIA and HPE. We're going to have three awesome sessions, and I can assure you and promise you're going to learn a lot. But first, for those of you who don't know the VMUG leaders, we're going to introduce ourselves. My name is Sarah Fallohiri, working as a senior consultant at Atea. I'm a co-blogger and co-video content producer at vLMS.net, and I have the honor to be member of VMUG leadership team. So Shahruz, please go ahead and introduce yourself.
Yeah, so my name is Shahruz Laiji, working as a solutions architect at Atea here in Stockholm. I'm a VMware specialist, so to say. I've been working with VMware for more than 14 years. And as Sadaf said, I'm also a blogger on vLMS.net, and we also produce some content on our YouTube channel, on vLMS.net channel. We also have another co-leader, Jasper Franzen. He's unfortunately not with us today, but Jasper also works as a system engineer. He's also a vExpert, and we would like to see him more on our events. Back to you, Sadaf.
Thank you, Shahruz. Regarding today's agenda, Frank Denneman is going to talk about machine learning infrastructure from vSphere infrastructure perspective, and then right after Jits, sorry, I cannot pronounce your family name yet.
Langedijk. No worries.
NVIDIA and VMware exciting times ahead, and then lastly, Alexander Ojanen gonna talk about accelerate insight from edge to cloud. And as you might notice, this Zoom session will be recorded, and then we're going to upload it to the YouTube channel of us, vLMS.net. You can find it there. So you need to only relax and enjoy. Frank, the virtual stage is yours. You can start.
Thank you, Sadaf. And thank you, VMUG Sweden, for having me. Let me share my screen. So here we go. So for today, I'm going to talk about machine learning infrastructure, and the title is a little bit weird from a vSphere infrastructure perspective. And what I mean by that is I'm going to take a look at machine learning, not from the algebraic side, but more or less from what a VI admin will see when the organization will take up machine learning. So what can you expect? What workload can you expect when the organization takes up machine learning? So how can you design your data center architecture so it can handle that workload efficiently? And so for today's agenda, we're going to look at what is machine learning today, how are you going to interact with it, what is machine learning infrastructure, the project engineering lifecycle of things, data science team, the personas behind it, and machine learning pipelines. So we are exposed to machine learning systems in everyday use. And some of you might already have a Google Assistant at home or an Amazon Alexa at home, or might even have a car with machine learning capabilities. They have some cars, high-end cars, they have voice-assisted navigation. That is typically provided by a company called Cerence, and over 200 million cars in the world are equipped with their technology. I think that's quite an impressive feat already. But there are also online recommender systems, something like Netflix. They try to recommend you what series to look next or what movie to look next. And then you have Amazon. And Amazon can sometimes be of a nuisance. I was rebuilding the house And I need to take a sip of my morning drink. My voice is a little bit shot. I have a little bit of a flu, so I sound a little bit off. Sorry for that. So Amazon, they have this recommender, and I'm rebuilding the house, and I made the wrong decision of looking for toilet seats on Amazon. And so for the next 3 months, I had these recommendations of, what about this toilet seat? And what about that toilet seat? I already bought my toilet seat. Sorry. So that can be this is much better. That can be improved. But the thing is, it is very important for their business need, because there are some online shopping systems such as Zalando or other online shopping merchants that really depend on those recommender systems. There's this online merchant who had this recommender system constantly recommending a woman's shoe with every item of clothing over and over again. And so what they did, the IT system or the IT organization, they only looked at the downstream components. So they only looked, is the service up? They monitored for, is that service up and running? They didn't look for what is it actually recommending. And so they calculated that over the 2 months that it was actually only recommending this woman's shoe, they lost over more than 20 million of revenue. So it's a very critical component, or it's becoming a very critical component of their entire revenue stream. And for companies like a Netflix or an Amazon Prime or a Disney Plus, that means eyes on the television. They want you to be on their platform to rake up their minutes instead of going to the competition. But you see that it becomes a real business model. And that's something that other companies, more traditional companies, are detecting as well, such as financial services. They are using it in fraud detection. They're using it to decide whether or not you're getting a loan if you are applying for a loan. And so if you go to a website like for a bank or maybe even a tech website, and you have you use those ML-driven chatbots, it will actually save them money. There was recently, IBM released a paper on the cost reduction of chatbots, and it appeared that organizations will have a 20% of cost reduction for their support organization when using chatbots. That's quite a bit of a cost reduction. And this is something that you see in other industries as well for cost reductions. Deutsche Bahn, excuse me, they use it to use ML in their locomotives as well to plan predictive maintenance. They look at the logs constantly to see whether they need to send a particular locomotive into their maintenance system to make sure that the machine is running perfectly. And it has provided them a 25% reduction in maintenance costs. Another thing which I think is very brilliant, they are outfitting larger stations with their what they call acoustic infrastructure monitoring system. They're picking up certain frequencies in their stations, alerting them that particular escalators need to be serviced. So they can service those escalators at a better time, making sure that the travelers don't get annoyed by it, because the last thing they want to do is they want to plan, or they want to have a escalator breakdown on the most busy part of the day. But they can also avoid having that escalator break down by just listening to that by just listening to particular frequency outputting by that escalator. And another thing what they do is they use vision and ML to look at stations that are not employed or occupied by their employers, so smaller stations, to see is there snow on the platform. So once the video cameras detect that there is snow on the platform, they send somebody over to clear out the platform for snow. That saves them a lot of money of having people to be there in the winter months when there's a snow period. And so Nike in the US is using modern technology with photo ID to have customers take photos of particular objects and use those colors to make or to create and customize their sneakers for them. And so that helps to cater to the need, or helps Nike to cater to the needs of the customer. And not only that, it also allows Nike to spot trends for their normal sneaker line instead of their custom Nike ID line. So they can spot trends across all the photo ID customers and apply that to the normal sneaker lines. But it also helps the marketing teams to specifically target or connect with their customers that are already buying Nike shoes, compared to people just going into a Foot Locker or any other shop that sells Nike shoes. So they have this collection of data that they can use by using machine learning technology. So you have this incredible new technology to your disposal to reduce cost and increase profit. So that is very promising for a lot of customers. And that's something that you see, and analysts see that as well. And so what we are hearing, not only when we talk to our customers, but analysts say that over the next 5 years, most of the applications will have some form of AI embedded in the system. And that can be applications that are built by the enterprise themselves, built by the organizations themselves, or just being bought, because that's another big thing that will happen, that there's going to be a whole ecosystems of application vendors that are building AI services or ML services, or just systems that are trusting ML services that are running somewhere else and plugging into those services. So ML is going to be a normal thing in the near and long-term future. So with that being said, we as VMware are also doing that. And so we have these 3 pillars inside VMware. So the first pillar is smarter VMware. So what we call smarter VMware is we are applying machine learning to improve our own efficiency. One of the things what we're doing is we are applying machine learning on hands-on labs participation. We're looking at which hands-on labs sessions are used, how long are they used, where are they struggling, and so what's the popularity of particular sessions and all those things. So we're trying to mine data right there. But what we're also doing is we're using it as bug classification. Sometimes a bug is incorrectly classified, and so it ends up at a different team, and it might be passed around between engineers like, do you know what you can do with this? And so that bug or that SR will take longer to fix. And so what ML does for us, it will look to see which team needs to look at this bug and makes the time to fix shorter. And it's very helpful for us. The column smarter products and services, we are trying to integrate machine learning into our products itself. So one of the things that we announced, I believe 2 years ago, is Project Magna, which by integrating ML into vSAN, we look at particular workloads and we can adjust the vSAN read cache for the workload characteristics of that workload and adjust it so that the cache is more aligned to that workload. Another thing that we demoed during this VMworld was OctoML. OctoML is a company, and we are working with them, that allows us to take a look at a particular workload that has been trained on a training infrastructure on a particular type of GPU, and typically multiple GPUs. So it's a massive infrastructure. And now that model is trained, has reached a particular accuracy. And now it has to be moved to the inference, where the inference architecture, so it runs in production, and it will be receiving unseen data, new data. And so that inference infrastructure is typically a lot smaller, and sometimes it doesn't have the same GPU architecture. It might be an ARM CPU or something else. And so that model is not optimized for that particular architecture. It's a completely new system. So maybe compare it to running something on an Intel system specifically for a particular register and a particular system, and now dropping it into an AMD system, something compared like that. Now, OctoML will use AI or ML system to optimize it automatically. So run that model through the system, say this is where it's been trained on, this is where it's going to run on for inference, and it will optimize it for you, instead of having data scientists and machine learning engineers to recode it and to retrain it for that particular inference system. Now, and then there's the last silo, smarter businesses, and that's where the majority of this presentation is all about, and that is how can we create a platform like the vSphere platform and the VMware Cloud platform to enable our customers to have them deploy their machine learning infrastructure to make them successful to run machine learning. So when we talk to the customers and the presenters who are going to follow me, they will have the same stories as well. The customers will typically talk about not necessarily finer details of like a particular GPU or a particular infrastructure, a data center infrastructure element, but they're more talking the CIOs or the CTOs or the head of data science. They're more talking about, I want to have a model that provides me the highest accuracy. If we're talking to a retail store that are creating cell scan registers or machine learning registers where you can throw your fruits on the conveyor belt, and so it will automatically scan that thing that is coming the way for that cashier. It needs to scan a avocado instead of an onion because that's a 50 cents difference, right? And so that accuracy will be the difference between a lot of money or losing a lot of money. And so that is the main topic of machine learning. But you want to have it as fast as possible because developing a model will cost money. The data science teams are not, the people are highly paid professionals, but also the infrastructure needed to deploy and create a model, that is also very expensive. So you want to minimize the time to get that model out. And typically you're not running a model, but once you're getting into the process of deploying machine learning, a lot of people follow. Same as virtualization. You started out with one virtual machine. In the end, you're now running 1,000 virtual machines or 10,000 virtual machines. It will never stop, for sure. And so you need to think this through. So you want to create this methodology in your organization that will allow you to keep that model development cycle short but precise. And now that gets us to the next scenario, stable prediction service. And that is, I want to have a prediction service that will stay relevant and is up all the time. And I will dig into that in the next slide. The next thing is explainability. It needs to be reproducible and explained. We call it responsible AI. And that's something the slide over we'll talk about that a little bit more. So when we're talking about stable prediction service, of course, we're talking about highly available infrastructure. So that's something that resonates very well with the audience right here. And of course, resilient infrastructure. It needs to be up and running all the time, and it needs to be able to take a hit. But what also is very important is that once you deploy a model in the real life world, it needs to stay relevant. Now, models will be trained on a particular set of data, and actually that means, in essence, a particular point in time. Now, the world moves on, and I think the most drastic example that we can actually provide is more or less the COVID example. So before COVID, the airline industry, the hotel industry, the entertainment industry, they were already using machine learning. But the moment COVID started, every model they used were completely useless because nothing was trained nothing in the data set was there to understand what COVID meant to the world. And so they had to retrain again. Now, this is a very drastic example, but it shows the essence of constantly retraining your model. Typically what happens is that over time, a model decays. The accuracy of the model is becoming lower and lower. So what will happen is that the data science team needs to determine a particular threshold that says, look, if the accuracy is below a particular number, we need to retrain the data with we need to retrain the model with a new set of data. So it is accurate to the current state of the world again. And so with that, you need, as an infrastructure team and as a team for the IT team, you need to come up with an automated process because you don't want to do this in a manual way. So if we look at the diagram, you're training the model, step one, and that model is moved to production. So we're going from training to inference. But at one point, that model is decaying, and we're monitoring that model. So we need to retrain that model again. So we need to bring in a set of data. So you want to capture the data, and you want to store it somewhere. So that's storage, and you want to keep storing that data. So that's an automated process. And then you want to retrain that model. So you want to trigger that. And then you want to bring in that model and replace that model again. So this is a continuous loop. So this is a CI/CD type of an approach, continuous integration, continuous development. So this is a standard approach from DevOps. So start to look at the DevOps methodology. So the Phoenix Project, a book, is a very interesting book to start at, to take a look at, and just start reading that book. It's an interesting book to read if you haven't read it already. If you haven't read it already, to companies some companies start with it already, but for some it's a year or 2 years out. This is a right time to look at these types of principles because DevOps will be an integral part for machine learning. So same goes for reproducibility and explainability. With the advent of GDPR and other regulations, a lot of companies need to make sure that your personal records are safe, but also at one point we need to explain that a particular recommendation or a particular result by an ML infused service is done in a particular way. And because of that loop that I just showed, we need to explain that a particular result is done by a particular model, but because we are always replacing that model, we need to store that previous model. And so we store it in, like the name says, in stores. So you have stores for your data set, for your previous data sets, and for newer data sets that you will use. You will have model registries. You will have registries for pipelines. And so you will have what we like to call a mall of stores in your environment. So this is also a CI/CD type of approach. You will have versioning for your data sets, for your models, and for your pipelines. So you have all these disciplines for machine learning. So it's a DevOps for machine learning. So you might well call it ML Ops. If you want to look into this, there are some incredibly good podcasts. The ML Ops community is one of those. I highly recommend that podcast to listen for if you are interested in that. Excuse me. So let's take a look at the machine learning infrastructure. So if we talk about infrastructure, if we talk about machine learning, typically a lot of people think about what I like to call, or what we like to call, the vertical stack. And the vertical stack is either in a virtual machine, but most of the time it's in a container. So you have an accelerator or just the CPU. So you have a CPU, a GPU, or in some cases even FPGA. And then you run your framework to create and train your model on. TensorFlow and PyTorch are the most dominant ones in the world, but there is also scikit-learn and Keras. And that's the basics to create your model. Now, of course, this is a very simplistic look of a vertical stack. I have a blog post written, I think already 2 years ago, where I actually show how complex a vertical stack is. I think I need to update it, but it's an interesting one. It's on my blog site, frankdenneman.nl, if you're interested in this. But this is the simplistic look for today. But now, if you want to create a model, you need to have data. So you start up by generating a training set or downloading a data set if you just want to start thinking with machine learning. And once you train the model, you want to make sure that it's doing its job. So you're using another new data set to validate it. And once the accuracy is actually good enough for you, you're going to move that model to a inference environment, and you're going to use pretty much the same vertical stack. And now you're going to provide that model unseen data, so to do the inference. Now, this is the vertical stack. And this already is very difficult to maintain and to run in your environment. But the key is data. The actual key of machine learning is data, because where does this data come from? And that is the key for most data center architectures, because there is this horizontal data plane, and later on it's going to be a horizontal model plane, that is very interesting, and that will actually create an incredible load within your whole infrastructure, because data needs to be wrangled into shape in order to make it able to be ready for the framework to be used to train on, to be used for training. So there are some steps that I listed out: ingestion, collection, validation, and cleaning, transformation, that are typically done by different platforms and by different systems all throughout your infrastructure. And this is the key. Data is flowing through your infrastructure, hitting different steps, hitting different machines, hitting different platforms. And that will be a very impactful element, a very noisy neighbor in your environment. But let's start off by looking at the vertical stack first and how you can do that efficiently before we're hitting on this topic. So before we can look at the vertical stack, I think the best way to understand how to create an efficient vertical stack is to look at the engineering lifecycle, because a lifecycle, a model engineering lifecycle is not like a waterfall. You're done with step A, then you go to step B. Once you completed step B, you go to step C. No, a model engineering lifecycle is actually a fluent process that goes back and forth, because we start off with an idea, and the organization says we have this business challenge and we're going to solve this with machine learning. And so the data science team will study whether it's actually feasible. Can we solve this with machine learning? So they're going to look at other projects. They might already have done another project, or they're going to look online to see, hey, did somebody else solve this problem? And so they're going to explore models, and they're going to explore frameworks. Which framework can I use? Which model should I use? And so they're going to test it on particular systems. Now, at one point, they need to figure out what type of data is floating around in the organization. What type of quality is the data? And do I need to transform it? So that's the planning phase. And so the next phase is they have the data, they transformed a little bit of the data. So they're going to develop the model. So they're going to use a little bit of data to train a model. And so they figure out we need more data. So they go back to the data exploration phase. They're going to go back in the organization. They're going to figure out who's sitting on that pile of data that I can use. And that goes back and forth a couple of times before they have this giant set of data. And then they're going to train the model that is really, that can really solve that business challenge. So once they have that massive data set, they're going to create this model that will provide that high accuracy. And once they have that high accurate model, they're going to put it into production. So that's the production phase. And so they have it in production, it's doing that inference, and now they're going to monitor it. And then they will see, now not every time, because not every model needs to be retrained, but a lot of models needs to be retrained. And so they're going to say, hey, we need to retrain again. And that's that continuous loop again, right? So some models, once they're out, it's fine, but most models, they need to be retrained. Now, think about that, and now think about how you're going to provide your data science team with hardware. Do I provide every data scientist a box underneath their desk with a lot of GPUs? And we think that there can be a much more elegant way, because if you think about the planning phase, they're testing an algorithm and there's no need for parallel horsepower. They're just tinkering. So you can have them, give them a virtual machine or a container, and they can just run their model with just CPUs, because there's no need for parallel horsepower. And that's where a GPU is so impressive. That's where you want to have a GPU, but maybe they want to have a little bit of horsepower. And so you can use NVIDIA vGPU, and hopefully Jits will talk about that. And that's just a fractional. So you can have with NVIDIA vGPUs, you can split up a GPU and have give half of it or a quarter of it to a particular virtual machine or to a container, and give the other parts to others. So you can share the wealth, something similar what we've done with virtual machines a long time ago. We can also use bit fusion, and that's remoting and pooling a lot of GPUs. So we install a client on a virtual machine or in a container, and then once the data scientist generates a CUDA call, so it's aligned with NVIDIA. Once it generates a CUDA call, we intercept that CUDA call and we send it over the network to a BitFusion server, which manages a lot of NVIDIA GPUs, and it will run that process on the GPUs. The result will be sent back to the machine, and the data scientist will get the result. Now, not every machine learning project needs to have low latency performance. Only particular vision projects need to have low latency response. So a Bitfusion solution can be very useful in a lot of the cases. And so it's a very efficient way of using those expensive resources. Pooling is a part of the DNA of VMware. So you will see that this is something we believe in very highly. Now, another solution is, of course, using the Horizon desktop. Create a desktop, provide that with NVIDIA vGPU, or use Bitfusion again, and deploy the full tool stack of the data science team in that desktop. They can even work from home. They can log into their desktop and use the resources in the enterprise data center. Now, same goes for the training phase. They have a small data set, but they can still use the same technologies I discussed before, right? Because they don't need to have that massive power, because they're developing it with a small data set and they're not pounding on those resources for hours and hours. They're just trying to figure out, is this the way to go forward with this model, with this framework? So they're running it in seconds or maybe minutes. Now, the key is the actual training phase to get the highest accuracy. So they're using large data sets and they're doing it for hours and hours. So it's throughput oriented and they want to have multiple devices. Now, in this case, you want to think about, can I create this cluster with full of GPUs? And can I come up with a scheduling mechanism that can give that particular data science team the access to most of those resources? And in that case, you want to have those full GPUs with NVIDIA GPUs for those virtual machines. Or in some cases, you want to have Bitfusion again, or maybe Horizon Desktop. Depends on the workloads that they are going to generate. If it's not a vision type of workload, maybe you're better off with Bitfusion or with an Horizon Desktop. It depends, but that's something that you need to work together with your data science team. I've had conversations with customers that were running more than 200-hour workloads on a particular environment. So a training job. So maybe you don't want to have that running next to your databases and other business critical workloads. So think about that when designing your data center architecture for your machine learning workload. Now, the production phase is inference, completely different landscape, because now it's all about having a workload that needs to be responsive all of the time and have a low latency. So we need to create an environment that is small but ready, and that's a very weird situation. So one of the things what we announced at VMworld was the project Santa Cruz. So that's something what you can check out at the VMworld site. But again, same type of technology, vSphere clusters of CPU, fractional GPUs by NVIDIA, or maybe Bitfusion. Another thing what you can also think about is ARM solutions. So that's something we also support. So there are multiple solutions possible. So in the end, think about it. Most people just start with, I want to just create bare metal systems with a lot of GPUs. Most of the time, it follows the same approach as what we have done in the beginning of virtualization. Move away from that bare metal thought and think about abstracting and pooling resources, because not every workload is active 100% of the time, eating all of the resource all of the time. And so in order to create such an environment, you need to work together with the data science team. And so it's a good idea to understand the personalities within the data science team. And so when I started talking to the data scientist in the beginning, I figured out that, hey, there's not a single data scientist. It's more of a spectrum of a user. I learned that there are some types that are, they look like, or they don't look like MacGyver, but they act like MacGyver. They like, oh, move out of the way, just give me a log on, give me a bare system, like a Kubernetes system and a user account, and I will do the rest, right? So for the infrastructure team, just set up a self-service environment that allows them to deploy a Kubernetes systems to their liking, and it allows them to log on, and that's good. But there's the other end of the spectrum. There's the Dr. McCoy type, where they say, I'm only here to create the best possible model in the world. And so you have to give me everything that I need. I don't want to deal with anything IT related. So what you need to do is you need to create this entire infrastructure that is completely curated and provide everything to the needs of their liking. And so you create a marketplace structure. So here you have the underlying platform where you have vSphere and you have your accelerators, and you can use Bitfusion or Project Radium, something we announced at VMworld as well. Bitfusion is aligned to NVIDIA. Project Radium is simply Bitfusion for any other workloads. Now, this is a little bit simplified, but overall, Project Radium, you can use it on other types of accelerators. So we have Tensu, of course, for Kubernetes, and now the self-service environment is there for the Dr. McCoy types, but also for the MacGyver types to make it easy to have this curated environment where you can go to your Bitnami application catalog, or maybe NVIDIA NGC or VRA, to pull down the bits that you need. So the ML pipeline or a data pipeline, or maybe use Project Cascade to deploy a object storage platform in your, or use it with your Tensu Kubernetes cluster, right? That's the environment that you want to use, and you can use with our solution. Now, the data scientist team doesn't only exist out of data scientists, they exist out of data engineers and ML engineers. Now, I know there's a lot of words in this. So what I want to show you here is that the data engineer is there to create the highest quality of data. And that's the output that is used as input for the data scientist, who can then provide with their work for the quality of prediction, the highest quality of prediction. Once that model provides the highest quality of prediction, now the ML engineer needs to operationalize the model. Typically, a model is written in a particular language that is not typically used by the application that is running in the production environment. So Python by the model, C++ in the application. So the ML engineer needs to repackage the model and deploy the model, and overall is responsible for monitoring the model, maybe only downstream, but overall they are there to do the operationalizing of the model. So that by itself is also a pipeline. And so what you see here is that they are working together, because once the data is being provided by the data engineer, the data scientist is going to train the model, but you will see that sometimes there's not enough data. And so the data scientist will ask the data engineer, give me more data. And so the data engineer goes back and it will give it back in the feature store. Now, something that I haven't talked about is features. Now, typically a feature is a collection of data points. So a data point may be, if you think about COVID, in a COVID database, a male is a data point, a height is a data point, but a feature might be all males that are vaccinated with a certain weight. That might be a feature. And so you have a collection of features that can create a data set that can be used to train a model. And so that is something you build in the feature store that can be used to train a model. And then once you train that model, that is handed over to the ML engineer. Model is deployed, model is served. At one point, once that model is decaying, you will bring that the ML engineer will talk to the data scientist. Well, hey, it's decaying, or maybe that is done together with the data scientist. Model is returned, model is retrained again. You'll see this is the process pipeline within the organization. Now, maybe we'll say, interesting, but how does this apply to my reality? And so I try to map that out to an infrastructure way. So here you have, let's use vision as an example. So here you have data source A, B, and C. Let's say it's cameras. And so they're generating video streams. And so you need to pick up those video streams and you need to place it somewhere. So you place those video streams in a centralized object storage platform. Let's use HDFS for that. Now you cannot use those video streams directly for model training. You need to change those you need to pick apart those video streams. So this is the data ingestion part. So now we go to the data processing part, and you need to move that data, those video streams, from HDFS into a data transformation platform. So typically those are Spark clusters, and you can use Project Capitola for that, something we announced at VMworld. So data transformation is in memory. So you need to have a lot of, you need to have a large environment, a large virtual machine. So you have monster virtual machines, or you can use Project Capitola. You can use tiered memory, maybe memory on a PCIe device, because not every memory has to be low latency. And now you can transform that video file into separate image files, and maybe make it in a different resolution, different file size, maybe change the color, whatever you want, right? But once it's set into memory, you cannot use it for model training. So now you need to move it again into your data warehouse, different system, maybe Tensor Greenplum or something else. If this wasn't vision, maybe if it was text, you can use it in a feature store. Like I said with that COVID example. Now, typically feature stores want to have a higher performance. So typically you're running it in an in-memory, in a key value store, something like Redis. Now, data warehouses are something slow, but you can run it as fast as possible, right? So it doesn't have to be on a slower system, but it can be in a fast system. But you want to bring it as close to the training cluster as possible. So think about vSAN, or maybe a pure system with NVMe Fabric. You want to have fast response. So the next step is creating a training cluster, multiple GPUs per host. Maybe you want to use Horovod for distributed training, or you can use VMware Bitfusion for that. So this is your cluster of CPU. So this is your model training exercise. So the next step is, once you train that model, you want to store that cluster. This is one of those training. This is one of those storing environments. One of those stores, one of the most popular stores is Selden, which runs on Kubernetes. So here you have a Kubernetes cluster again. You need to store it somewhere, so you want to have an object store environment. S3, Minio. You can use Minio for that. This is something what we do with Project Cascade. So the next step is, now we're going to move that highly accurate model to the inference side. Because it's trained on this massive training cluster, and now we're going to train it, we're going to move it to the edge environment, we want to optimize it. So we can use OctoML for that. So during the process, we're going to run it through OctoML, and now we're going to place it on our model serving platform. Either we're going to incorporate it into an application, but most of the time nowadays, it is run as a microservice. So again, a Kubernetes environment, and because it's a microservice, you need to typically use a service mesh for that as well. So think about an Istio. So here we have another Kubernetes cluster as well. Now you can use that microservice and attach a website to it. And the next step, of course, is to monitor it. You want to monitor the backend, the downstream part, so the Kubernetes end of it. So you want to use Grafana and Prometheus, but you also want to monitor the upstream end. Like I said in the beginning, with that fashion retail store that was showing only that women shoe and lost almost 20 million euros. You want to use upstream monitoring as well. So you can design you can write your own monitoring tool or use something like Prometheus or something else again. So this is just a simple pipeline for customer for one model that runs in the environment. This pipeline will be deployed many times over. You can still use those systems like Spark and like your GPU clusters or many different other pipelines. But you will see that there's this lot of data flowing through different systems, different platforms in your environment. So you need to think about the impact that that data has on other systems, on your virtualization environments, and typically data that is pushed in a virtual machine or in a container that is running in a Kubernetes cluster, that is typically just handled by x86 cycles. So one of the things that you can also look at is Project Monterey, using SmartNICs as data processing units to get that network acceleration offload. By moving data from ESX host to another ESX host, you're allowing the DPU to handle that data processing. And so I can talk about hours about Project Monterey, and hopefully Jits has something in his presentation about DPUs, or otherwise he can point you to resources from NVIDIA about Project Monterey. But this is something that you also want to check out if your organization is going to look at machine learning, because overall, machine learning is a lot about data. So what I want to give you as key takeaways: investigate DevOps methodology and CI/CD pipelines. Begin with that, because that is the overall way that your organization will start to deal with your data science teams. The container is the lowest level of abstraction. So look at Kubernetes, start to investigate Kubernetes, start slowly by looking at that. Think about creating a self-service environment with rich marketplace structures. Start curating the applications that are needed for your data science team. Like I said, data is the first-class citizen. There's a lot of data, so prepare your infrastructure for it. Figure out where you want to run particular services, like where you want to train, where you want to keep your data. And each phase of the life cycle of the ML workload requires a different platform. Don't go brute force, give everybody GPUs. Maybe that's something that this thing is that Jits doesn't like what I'm going to say, but there might be a very better way and more efficient way of going around than giving everybody. Like I said, the bare metal days were 20 years behind us. Let's not go over that again with machine learning. And with that, I would like to thank you, and I'll give it back to the organization.
Thank you very much, Frank. It was a really great presentation, and it's always a pleasure to have you on board.
Thank you for having me, and hopefully it was enjoyable with this voice.
Sure, it was. All right. So,
guys, if you have any questions, Frank's going to be with us until the end of the session. So please ask your question if you have any.
You can also write your question in the chat box or in a Q&A section. I was looking at it, but there were no questions.
Yeah, it was empty.
If there are any questions, please feel free to reach out on Twitter, or I'm still here, so just put them in the chat.
Thank you. All right, then I would like to ask Jits to...
Yep, sure. Let me share my screen.
Yeah.
And maybe you can confirm whether my screen is coming across.
Yeah, it's perfect. Okay. We can see you.
Excellent. Excellent.
Thank you.
Sharuz and Sedat, thank you first of all, and of course everyone at the VMUG over in Sweden. But thank you for providing us the opportunity to meet you all. Unfortunately, virtually, but maybe one day we can do this face to face again.
Yeah, maybe next year.
Sure.
Yeah. Well, I'm looking forward to it. And also, thank you, Frank. Just the Dutch pronunciation, right? So it's almost like well, 2/3 is Dutch of the speakers today. So, was a great presentation. I enjoyed it very much. Even also the last part, right? I mean, VMUG is all about, a true honest story without too much marketing fluff. So you would only need a GPU when their use case really desires GPU or hardware acceleration, of course. So I don't mind. Of course, this is the VMUG in Sweden. So I'll be talking about VMware and both NVIDIA, of course. And throughout this session, I will be talking about a little bit demystifying artificial intelligence. Although Frank already mentioned a lot of things about machine learning and maybe a little bit also on deep learning. Of course, since this is also an NVIDIA presentation, I will be talking about hardware acceleration, GPUs, and also the DPUs, as Frank mentioned at the end. And of course, also the exciting times ahead. What is it that we do together? And, maybe what is an opportunity for you as a industry expert with VMware today? That's what I'll be covering, these three topics. First of all, let me briefly introduce myself. My name is Jits Langedijk. I'm a partner solutions architect at NVIDIA. Please reach out to me. My email address is on the slide. If you have any questions, always happy to help. And let me just quickly kick off to the first part, the demystifying artificial intelligence. And AI is maybe... Well, it's more like maybe that's already a container, right? A containerized bus terminology that we'll be using for a couple of years already. And to be honest, AI is not something that is particularly new. So already in the 1950s in the Dartmouth College, they were talking about artificial intelligence, and basically they were talking about, or maybe dreaming about, a supercomputer that mimics all the characteristics that we have as human beings. So when we're talking about natural language processing, this is something that we as human beings train with our children, and now I can talk to you and you can understand me. But this is, of course, for a computer, as Frank also mentioned, like voice-driven commands in cars. This is something, more challenging for cars. So artificial intelligence is something that is definitely around for quite some time. It's being the supercomputer that mimics all the characteristics of a human being is something that only has been achieved in Hollywood. But today we have a lot of narrow AI solutions, like the Alexa that Frank mentioned, or maybe some autonomous driving cars that we're all familiar with. So artificial intelligence is like you can divide it up into two segments maybe. First of all, there's machine learning, which is a little bit older, and then there's deep learning that gained a lot of traction somewhere 10 years ago. So machine learning is something different compared to deep learning, and let me just briefly try to explain this. And I think maybe Frank also mentioned this a little bit with data points and feature abstractions. So if we look at machine learning, this is more or less the traditional approach. Consider this additional approach to performing computer vision tasks such as image classification or object detection. A domain expert trained in computer vision comes up with a set of rules to extract features from this image, such as how many wheels it has, or how many headlights, how many corners does it have, or edges, or the color. And based on all those feature extractions, you would come up with, this is a car or a coupe, it's a vehicle, it's a red vehicle, etc. So as you can imagine, it can be a tedious and tedious job and requires a lot of trial and error. So this is typically what we do with machine learning, which is great, and especially for a lot of use cases, it makes a lot of sense. But the difference when it comes to deep learning is the fact that with deep learning, of course, you still need a domain expert, but more the domain expert on frameworks and on how to prep data, for example. So what we do with deep learning is something different, and I always compare this again to what we do with our kids. I think for those who have kids, and maybe you've been, well, we've all been a kid ourselves, but maybe in your childhood you had these little books where just on one page there was a ball or a key or a house or a car, etc., and only one word was written underneath it, explaining what the image was all about. And basically this was what we did, was training we trained ourselves to look at these images, and each and every time we would see this image, a labeled image, because the key underneath it said it was a key, and maybe you had different books and you had different keys, of course. So, but in the end, what was happening is basically that in your brains, between neurons, there were built up connections between those neurons, and this allows you as a human being to now, if you see a key that you have never seen before, maybe in a different form, and maybe from the first view at this key, you do not really recognize it as a key, but on a second view, you say, okay, maybe this is a key. Basically, you're activating these neurons. And this is something that we do with deep learning as well. We're building connections, we're building these feature extractions to recognize what is a key in this example. So we're using a lot of data in order to train a model, and I'll explain this a little bit more. But first, why is it that we do such things, and what kind of inputs do we have? Of course, we have a lot of inputs like images, video, but also text, and of course also audio. But there are more examples for this, as you can imagine. And what we want to do is maybe we want to detect something, or we want to classify something, or we want to segment something, or predict, or recommend, as Frank also mentioned, the recommender systems, like NVIDIA Merlin, for example. So, how does this look, for example? If we look at neural networks that do classification and maybe localization, so the bounding boxes around something, or object detection, various objects within an image or a video stream, but also image segmentation. And as you can understand, and it always speaks to our imagination the most, at least from my perspective, is the self-driving car. So this is something that we do at NVIDIA as well. This is not because we want to build and create a self-driving car that would be available to the masses, but this is something that we do in order to train ourselves to learn what all our partners, also the car manufacturers over in Sweden, what it is that they will be faced as a challenge maybe next week or next month or next year. So this is how we can help them understanding their challenges. So if you look at a self-driving car or the autonomous objects, you take a image, maybe just a camera feed, for example, and this is what a car would see. But basically, this is the information that you take out of such an image in order to make decisions. So this is the inferencing that Frank mentioned. And talking about training and inferencing, again, let me go back to this deep learning approach and methodology. So remember, as I mentioned, our brains work with neurons and connections between neurons, and basically a neural network, a deep learning neural network, we represent it as the same. So we have an input layer, so these are the little dots on the top layer, and we have an output layer all the way down on this model. So this is a very easy model with only two hidden layers in between. Basically, all these different green dots, they represent these neurons. What you would like to do is create connections between these neurons that the internet was built for cats and dogs, especially for cats. So what you want to do is use a labeled data set. So a labeled data set means that you, and of course, this is all about training with, well, supervised training, so with a labeled data set. There's also unsupervised learning where you just throw data at it and, well, we'll see what comes out of it. Well, there's more nuance to that, but in this particular example, you would use a set of data with images of cats and dogs and all labeled. So again, this is the little book that you had as a child maybe. And what you would do is you feed all these images through a neural network, and the neural network will, all the different features, extractions will tell whether this image is a cat or a dog. And because it's labeled data, at the end, at the output layer, you can do the check on whether the neural network did it correctly, yes or no. And of course, you would do this multiple times, multiple iterations or epochs. And also, you could, of course, when a neural network came out with the wrong, well, let's call it conclusion, you would send it back to the neural network in order to reinforce certain connections between those layers and maybe weaken some other connections between these layers. And very important here, when it comes to also maybe one of the big differences between machine learning and deep learning is that, or well, maybe more on high performance computing, if we take that side of the spectrum. With high performance computing, you want to be as accurate as possible. Basically, you want to be 100% accurate. So you want to do all your mathematical calculations of a strength calculation for a bridge, for example. You want to be as accurate as well as possible. As where specifically with deep learning, and in some cases also with machine learning, it's all about probability. So a neural network will never tell you like, this is a cat, or this is a dog, or I don't know, this is a duck. It will always tell you like, I'm 90% sure this is a cat and I'm 60% sure this is a dog. And of course, well, the higher number wins. Or basically you use that outcome as an input for, well, your next step. Usually it's a trigger or a representation of something. So it's always about a probability. And of course, the more training you do, the higher probability will be. And at the end, you're well, better in predicting than a human being is. Because if you look at medical imaging, for example, a doctor in a hospital looking at X-ray images, he or she will never be 100% accurate. I mean, well, people will make mistakes, even unfortunately in these situations. So when you use deep learning, for example, to recognize certain patterns in X-ray images or different images, medical imaging, it's all about this accuracy. And of course, with a deep learning neural network, you can reach with the proper training a higher accuracy than human beings can achieve. So, but in the end, you've done this multiple times with a training set, and of course, as you can imagine, this requires a lot of computational resources. And of course, especially when it comes to recognizing images or classifying text, etc., or maybe speech, hardware acceleration with GPUs really speed up this process. Can it be done on CPU? Yes, you can, but in some situations there is, or most of the situations these days, there's simply too much data or too much features to extract. If you look at GPT-3 in a natural language processing, or BERT, a natural language processing model, 175 billion parameters in such a model. So can you imagine how long it will take to train on that data just on CPU? It will take you years and years, and by the end, when you're done, basically the data is already outdated, and you need to infuse it with new data. So this is why GPU acceleration is very important there, of course. So once you have trained the model, and as you can see here, some of the neurons have grown and connections between them are stronger, and it has a high accuracy. Then all of a sudden, you have a trained model which you can take into production. And this is, as Frank also mentioned, the inference phase. So this is where you use, and maybe Shazam, the app which you can use on your smartphone that recognizes the music that is playing. that's just a simple app, and of course it uses GPU accelerated resources in the data center, but much less resources, and with that GPU acceleration is required just to do this inferencing phase. But again, it's very important to keep training those models, and I was very happy to hear Frank mention this. So you need to things change. The accuracy needs to increase. So you need to keep on training. So this is a little bit the differences between machine learning and deep learning, and how you kind of understand these two approaches on basically using data and doing something smart with it, making better decisions, and also in a shorter time frame, of course. Usually it all comes down to that. So there are of course a couple of challenges with machine learning and deep learning, or AI in general. We covered the different personas when it comes to machine learning or data scientists, or the data scientist, the researcher. They are constantly working on something new. Their work is never done, so they need maximum flexibility, and usually they also need maximum amount of resources. Basically, when you ask a data scientist or a researcher what it is that they need, they will come up with, I need a supercomputer, which is great, and this is an example of the NVIDIA HGX baseboard that you can find in an HPE Apollo system, for example. And it would be great to provide a supercomputer like an Apollo 6500 to each and every individual in an organization. But yeah, reality tells us things are different. And when it comes to different situations, I also want to mention that we have different stages, and I think Frank also mentioned different stages in his presentation. And I want to just dumb it down to basically we have a development phase, a training phase, and a deployment phase. So I think in the previous slides I already talked a little bit about the training phase and the deployment phase. The deployments, this is where you do the inferencing, and each and every phase has different needs. So when we talk about deployment, you do not maybe need as much as computational resources and with that GPU acceleration as you would need with training. So with training, you need a supercomputer. With the deployment, the inferencing phase, maybe you need a fractionized GPU. Or you would need something as Triton Inference Server, where you have all the flexibility to provide the right amount of resources to the different inferencing jobs. But there is also, of course, development. This is where the prototyping phase takes place. This is where you have a small set of data, just a subset of the entire training set. And this is where you, as a data scientist, you would try out the algorithms, the frameworks that you are aiming for, and you will just see whether this is working or not, whether you're on the right path. So it's important to understand that there are different stages, and with that also what I always call the different requirements when it comes to the computational spectrum. So we have a light compute. This is something that you could maybe run on a Windows machine, and this could very well be a virtual machine just in your Horizon environment, for example, GPU accelerated with NVIDIA vGPU, or maybe you have a pass-through GPU and more compute power or GPU power is required. But this is something that you could definitely build on top of or within a Horizon, a typical VDI environment, basically. And this can either be Windows or Linux. And then we have the more general compute use cases. This is where the complexity increases. This is where you maybe need double precision math, like the FP64. So the double precision that we provide in GPUs. This is where you need more resources, more GPU resources, maybe multiple virtual GPUs assigned to the same virtual machine. This is where you would leverage the error correction code memory in our GPUs, and then of course another step up is the classic high-end compute workloads. So this is where you would typically place a supercomputer. If we take a look at especially the light compute, and also in the previous slide with the development phase. Well, you could argue that, and I think this is something that we're all familiar to. Like we have a VDI environment to cater Windows 10 virtual desktops. We have different clusters within our environment. We have our control resources. And maybe next to that, we're already building something based on an A100 GPU, just specifically to run some Linux virtual machines for our data scientists. So now, instead of just using a Windows 10 desktop maybe to do their office productivity work, they also have access to a Linux-based virtual machine where they can just start prototyping with their the project that they're working on. And of course, due to the fact that it is all based on virtualization technology, you could also, of course, spin down those resources, consolidate it all into to a single cluster, or maybe even a couple of hosts, and then you can spin up big virtual machines. And this is more like the VDI by day, compute by night use case. And just to do the heavy lifting. This is where you would do more the training work, so not the development phase, but this is really where you would do the training. So I think or I don't think so, I'm convinced that with the flexibility that virtualization and with that VMware vSphere ESXi, of course, has to offer, with the virtualized GPU, you have all the tools available to address different use cases within your organization or at your customer. So really making use of all the investments that has been done there. As I think Frank already mentioned a couple of use cases where machine learning and deep learning was applied, and I had a couple of those prepared. And as I already mentioned, Shazam, the app that's basically doing the inferencing work, or represents the inferencing work that runs on in this case some older GPUs, but it's still doing a great job, and they're investing into new GPUs as well. But this really provides a quick and good answer, and the same is what you do, of course, when you're talking to your Amazon Alexa. They trained with all the speeches in different languages and all the different pronunciations of what we use as human beings in order to make sure that it exactly does. I'm always a little bit scared when I give some commands here, of course, that she will start talking to me, so I should have muted it. But also when we address the recommender systems, an example of a Dutch airline that has a very small group of agents that is doing the social media services. And well, I don't know today, but especially pre-COVID, they were having like 15,000 conversations each week on different channels. And basically what they have done is when someone asks a question, a machine learning algorithm is analyzing this question and detects whether it's very urgent or it's something that can wait a little bit longer, and it already suggests an answer to the agent, and the agent will choose just to admit it and send it back, or he or she can personalize the message and change a couple of things. So machine learning really helps them to provide responsive answers to all of the passengers that they service at KLM. I talked a little bit about machine learning, deep learning, and why GPUs are that important. Maybe this is something that I want to call out as well. Sometimes, we tend to forget that why is a GPU that important? And of course, NVIDIA is known by the gaming industry, and luckily, especially for a VMUG audience, I think, or I hope most of you is familiar with the vGPU solutions. But let me tell you a little bit on why NVIDIA is now all of a sudden that important. And I think maybe you can guess already, it's all about the data. Frank mentioned like data is a first-class citizen, but there's so much data available. If you look at predictive maintenance, as Frank also mentions with Deutsche Bahn, and we have others in Europe as well, that they're based on a delay from a certain train, that they can immediately calculate all basically the snowball effect of a delay of a single train, that they immediately can act on this effect and minimize the snowball effect on other trains. So they can recalculate the entire train table of all the different trains, and this is an example that's been done in Switzerland, for example. But you need so much data, and in order to analyze all this data and make better decisions in a much shorter time frame, of course, you need a GPU to analyze all this data. So this is why NVIDIA is all that important in machine learning and deep learning. And computational acceleration, whether that's CPU or GPU, what we have seen is that the increase of computational acceleration purely on CPU is starting to level off. And this is where the GPU really kicks in providing this additional horsepower. And of course, you need to keep in mind that it's not about replacing a CPU, definitely not. You will always need a CPU next to the GPU. But it is important to understand that, an application, and this both counts for applications where it's all about graphics acceleration, as well as for those applications that are about computational acceleration. They need to be able to address their code to a GPU. So, and luckily the amount of green lines within application code is increasing, almost on a daily basis, but especially when it comes to deep learning, machine learning, maybe it's even the other way around. You would need, like 80% of the code is running on the GPU, and 20% is handled by the CPU. So that's why NVIDIA is that important in this space. We are a platform company that delivers, of course, the GPUs, the hardware. This is where it all started. But based on that, we have a huge software platform as well. And this is sometimes, especially for the data scientist, that's a hidden gem. And especially if you look at the application framework. So maybe after these VMUG sessions today, you can have a quick peek at developer.nvidia.com, and you would see, like, for many different verticals, many different use cases, we have lots and lots of frameworks available, SDKs, pre-trained SDKs as well. If you look at, Metropolis is also on the top layer. This is a intelligent video analytics SDK with the DeepStream SDK, a pre-trained model that you can use and infuse with your own data, just to accelerate the data science and research projects. So there is a lot of things that are available, and I would definitely recommend just to have a look there. It's not just about the GPU, definitely not. I think the whole change is, of course, it's all about the software that's available on top of these GPUs. However, I do want to mention a couple of things about these GPUs. So as you would see here, this is our lineup of GPUs. GPUs specifically more developed towards compute workloads. So the A100 and the A30, those are two GPUs which you can only use to do computational acceleration, whether that's high performance computing or machine learning or deep learning. But you cannot do any graphics acceleration. So if you're building a VDI environment to do Windows 10 with maybe some 3D CAD applications, A100 and A30 are not the GPUs that you would choose for this use case. On the right side, we have the A40, A10, T4, and A16. Those are the GPUs that can both do graphics, but also, of course, computational acceleration. So you might wonder, why is the A10 and the T4 why is there a bounding box around it? And the reason is, we have some supply constraints, especially when it comes to memory. So basically, A10 and T4 are not really available. I know, and luckily, our strategic partner HPE really stocked up on T4s. But if you're working on a project, either with A10 or T4s, really reach out to your OEM supplier and ask them about the availability. As you would ask us, it's A40 or A16 today, what you should aim for. So, and I think maybe the A100, A30, those are two GPUs that both support multi-instance GPUs. So next to the vGPU solution, where you would fractionalize a GPU and assign different portions of frame buffer, of video memory to certain virtual machines. With the A100 and the A30, we have the multi-instance GPU capability, and this allows you to carve up into a maximum of 7 instances with the A100 and 4 instances with the A30 to really slice up the GPU and assign a isolated with quality of service instance to a machine or to a job. So this is a different technique, as where vGPU, of course, you would have all the users or all the virtual machines using the same GPU resources simultaneously and basically queuing up. As where with the multi-instance GPU technology, this is not the case. Each and every MIG instance gets its own amount of streaming multiprocessors, memory, etc. So that's a big difference there. Of course, it's important to understand how you should transition from your current GPU infrastructure maybe to newer GPUs. So this session is recorded. I'm also happy to reach out the slides via the VMUG leaders. But if you look at this slide, especially when it comes to deep learning, machine learning, high performance computing, artificial intelligence, data science, this is where you would typically use the double precision GPU, so the V100, B100. T4 is not a double precision GPU, but it's an ideal GPU to do inferencing, of course, because it's a much smaller. You could do inferencing at the edge. But in these situations, you would typically go to an NVIDIA A100 or the A30. And also, when it comes to a virtualization environment, you would look at NVIDIA AI Enterprise, which I'll be addressing shortly. When it comes to the mid-range and high-end virtual workstations, this is where you would use the A40 with the RTX virtual workstation licenses for vGPU. And then the A16, a relatively new GPU, will become available also with HPE pretty soon. This is a GPU that some of you might recognize from the M10 era. So this is a physical GPU that contains 4 physical GPUs on the same board. So kind of similar to the M10. We doubled the amount of memory, we doubled the amount of decoder capabilities. So it's a much more powerful board, as you might expect, of course, from a newer GPU generation. But this is definitely a board aiming at those high user density use cases for your office productivity use cases, and maybe also a little bit the entry-level virtual workstations with the RTX virtual workstation licenses. Important to understand, A100, A30, A40, and A16 are the boards that you would typically aim for today. When we talked about hardware, I also promised you to address the data processing unit, of course, and especially in relationship to VMware. So the data processing unit is something more than just a smart NIC. Of course, the idea of having a network interface in a server chassis that can offload certain tasks from the central compute unit, the CPU and the system memory, etc., is not something that is new. But definitely what we have done together with, of course, due to the fact that we merged or we acquired Mellanox together, and Mellanox was already working on this. Of course, Mellanox had the Connect X6 network interfaces. These were already the programmable interfaces, but now what we've done is put more ARM cores on this and acceleration engines with with GPU capabilities in the future as well, as you can understand. And this is, of course, all about offloading certain tasks from a machine, from a server. So if you look on the left, this is your traditional approach, and maybe if we stick to to VMware, this is where you have your vSAN maybe, and your software-defined networking, your NSX. This is all consuming resources from the compute unit itself. So the CPUs and the system memory, and of course. You could argue that the resources are sufficient today, and it's definitely fine to run it in such a situation. Especially since the idea of offloading this to a network interface came from the big hyperscalers, so AWS, for example. But then again, it's not all about freeing up resources, which is very important to run your virtual machines and maybe your next generation applications or your containers. But it's also about accelerating. It's also about isolating and increasing security, of course. If you look at software-defined security, of course, when you run this on the right side on a DPU, you can already deal with all the threats on the interface itself. So first of all, you're not only offloading these from the central processing unit, but it's also increasing the security, because the malicious code will never reach the CPU or the system memory. And also the other way around, when someone opens up some malicious software on a virtual machine, and it can easily spread the network, it will be isolated due to the fact that it will be blocked by the data processing unit, or basically the data processing unit is facilitating the security features that run on that level. So this is something, of course, that we have announced together with VMware, Project Monterey, and this is not only just for virtual machines, but this is also something that you could do for bare metal deployments. This allows you, especially if in some data science situations, people still require maximum amount of performance, and they don't want to decrease, I don't know, maybe it is 0.0001 performance decrease with virtualization. They need a bare metal deployment, or maybe that's the only supported configuration. They would go with bare metal servers, but you would still, from a admin perspective, you would have the same approach when it comes to management and also deployment of your networking security and firewalling and vSAN and host management, of course. So with a DPU, you can both address a virtualized server as well as a bare metal deployment. So this is something that we do with VMware, but there was also another great announcement, or let me just keep it to announcement, and this is all about VMware and NVIDIA together, and this is all addressing everything about basically everything that Frank just mentioned. Artificial intelligence, machine learning, and deep learning are already that important, but will become even more important over the next couple of years. So each and every application, each and every industry, each and every customer will be impacted, whether you, as Frank mentioned, whether you develop it yourself or whether you use it. It is or will become even more important. So when you look at human resources, for example, the acquisition of talent, maybe we all have been through this, but going through maybe hundreds of CVs and just picking out the right one, that can be a time-consuming job. So AI will help us with that. Marketing and sales, AI also will determine on pricing, for example, or AI, as Frank mentioned with the example of the women's shoe, losing out business, of course. Customer services, I mentioned with the example of KLM. AI is something that impacts each and every business. However, what we do see is that a lot of AI projects, they fail. There are quite some risks. You need the right you need the right equipment, and maybe you need to integrate with an existing infrastructure, but you also need the right amount of performance. If something just runs too long because the computational acceleration is not available, it's not turn out to be a great success. And then, of course, when something is implemented, you need to scale it. You need all the flexibility that is available within your infrastructure in order to scale it. So this is what we addressed. And if we look at the data center infrastructure, maybe today on the left, we see a lot of like siloed approach. So we have a CPU-only backend infrastructure or cluster. And then we have particular clusters or silos for particular purposes, whether that's VDI or training or inferencing. And what you, in the end, would like, of course, is a unified environment that can basically serve all these different requirements. And the challenge is, of course, also that, as I mentioned with a data scientist, they can tell you what they need today, but they cannot tell you what they need tomorrow or the day after. So it's always a big challenge. And of course, what you want is, and Frank summed it up already, you want like a self-service portal where a data scientist can just make it or select a particular instance in order to train a particular model. So for that, you need a infrastructure running on certified servers. You need all the management and orchestration. Well, this is something that definitely VMware can help you with. And on top of that, you need something that we call NVIDIA AI Enterprise. So this is where we provide all the tools and frameworks. So as I said, the the NVIDIA AI Enterprise solution is a 3-layered stack. It contains the mainstream service. So take your 2U DL380 or 385 from HPE, fully NVIDIA certified with the DPUs or the Connect X6 Smart NICs, and of course the NVIDIA GPUs. Just your mainstream server in your data center, and on top of that, of course, everything from VMware. So this, of course, starts with the virtualization layer, but it also allows you to use all the flexibility with live migration, load balancing. You have the life cycle management, especially if you look at this self-service portal. But more importantly, it's also the Kubernetes and Tanzu Kubernetes grid that you can integrate into this solution. So I always, especially for those admins who are more focused on end-user computing and providing desktops, allowing individuals within an organization easy, secure, and reliable access to their data and applications. This is more or less the same, but then for a data scientist. So if we zoom in into the top layer, the AI Enterprise part from NVIDIA, this is where we provide the tools such as NVIDIA vGPU. So again, providing all the flexibility with GPU virtualization on top of VMware ESXi, Magnum IO and NVIDIA CUDA-X, all the tools that you would need to optimize your infrastructure, whether that's with what is it? The storage parts or the CUDA libraries. And on top of that, we also have the NVIDIA GPU operator and the network operator. And as you can understand, these are tools that allow you, from an administrative point of view, to basically create profiles for your GPUs or for your network components, and to distribute it to all your mainstream servers. So if you would add a new server to their environment, you can easily, from the GPU operator, network operator, make sure that everything is aligned, but everything is also kept up to date. and especially for data scientists, the top layer, so all the tools and the frameworks, what we have done here is we have the NVIDIA GPU Cloud, NGC, as Frank mentioned. This is a big repository of all kinds of tools, frameworks, pre-trained models, etc., which a data scientist can use. And what we have done here is with the NVIDIA AI Enterprise offering is that we took TensorFlow, PyTorch, and Rapid, so 2 deep learning and 1 machine learning framework, and fully optimized it, certified it, and supported, of course, within this entire stack. And next to that, we also have the NVIDIA TensorRT and the Triton Inference Server. So 2 tools, 2 tools available just to make sure that also the inferencing with TensorRT is optimized when you go into production, but also the inference server where you have all the flexibility to create inferencing instances. So as mentioned, NVIDIA AI Enterprise, fully optimized performance on VMware vSphere, so it's certified for VMware vSphere, and fully supported. So it's not only about the hardware and the software, but also about the frameworks that we deliver on top of that. I think I'm already 1 minute over time, but I would really encourage you all to have a closer look at the NVIDIA AI Enterprise offering that we have, which allows you to deploy it with confidence and for your colleagues within an organization or at your customer, boost the AI performance, and also allow you to have the ability to scale out within your VMware environment and to easily address all those needs that the data scientists will come up tomorrow. And I cannot emphasize this enough. I'm convinced, especially since the fact that many of our VMUG members are pretty familiar with the NVIDIA vGPU offering that we have since 2013. Many of you, of course, have implemented this and upgraded this. And basically, what we have done now with extending the virtualization technologies for different use cases, we opened up with NVIDIA AI Enterprise. We opened up more opportunities for our partners, but especially for our customers. So based on the same infrastructure principles, you can also offer workloads, or you can also offer instances to run workloads for any data science, machine learning, deep learning type use cases. So I would definitely want to emphasize the fact that all the knowledge that is already available within the community, at our partners and at our customers, this can be reapplied also to cater all these instances for the data scientists within an organization. And I think with that, I'm gonna hand it over to Alexander. And also for me, the same applies. If you have any questions, feel free to reach out, and happy to help. And then over to you, I think, Alexander.
Thank you, Jits.
Thank you.
It was really good.
I'm going to share my screen, so please let me know when you can see it.
Please do that, Alex. Yeah, we can see your screen.
Okay, perfect. So thank you for the opportunity to speak to you at this VMUG session. I'm really excited, and thank you, Frank and Jits, for the great presentations. My name is Alexander Ojanen, and I'm a category manager with Hewlett Packard Enterprise here in Sweden. And really, before I start, I mean, personally, I think this is like the most exciting development within tech and society and the way we live. Really, how we're going to use AI to cure diseases or eradicate hunger or just enhance everyday life. So that is really exciting. There's no better time to be alive than today, and tomorrow will be even better, I think. So it's an interesting topic. So I'm going to talk to you about our edge-to-cloud systems that are purpose-built for AI applications. But before we go into any details, I would just like to start to talk about data. I mean, we all know the importance of data. You could even argue that it should be included in companies' financial statement even. And if you listen to the analyst firms, all of them say more or less the same thing. By the end of this decade, we will have two types of companies. Those that are data-driven, meaning they are harnessing their data and analyzing their data, and those that are out of business. And I think Jits said like every industry will be disrupted by this in one way or another. And as Frank said, like some have already started, but if you have not started yet, this is really the time to do so, I think. And historically, most of the data have been created within the data center, but that is really far from the reality we live in today, where the vast majority of the data is created outside of the data center, really by everyone and everything that is connected. You know, that could be any type of sensor in anything we use in our everyday life. And the amount of these connected devices with different sensors and people and the amount of data, it's really exploding. I think we can read about it every day and we encounter it every day as well. And to gain the value out of this data, it needs to be analyzed. And that is what's driving the need for AI. And in many cases, actually, to gain the actual value out of this data, it needs to be analyzed and acted upon in real time. And you have already heard the example of the driving car. I mean, that is really a good example because you don't want to wait on the data to come back to the car to avoid that accident, right? You want that to be instant. But it could also be like video analytics, and maybe at the construction site where you want to make sure that no one walks under a crane when you do a heavy lift. You don't want to wait on the analytics of the video stream to come back, and that takes a couple of seconds. It needs to be instantly. And you may have heard about the phrase data gravity, which essentially says that the more data one has, the longer it takes to move it. And this is what's driving the need for what we call edge computing. And I'm going to show you a short clip, just 2 minutes, so you can kick back and relax. And we'll illustrate this a bit more.
Let's talk about the edge. It's the place where data is exploding, and where harnessing that data has the power to connect, problem solve, and uncover insights. Where decisions are made in real time so businesses can create more immersive experiences, new services, and unmatched efficiencies. It's the place where our world is moving right now. But here's the truth. The edge isn't all the way out at the edge anymore. It isn't just a fringe or faraway place. In fact, it isn't some place, but every place. It's where smart cameras can turn slow lines into finish lines. Where an AI-powered X-ray can find cancer faster. Where connected machines on a factory floor can communicate 5 terabytes of data a day to create the things people use every day. So much is possible when businesses successfully innovate at the edge. So how do you get in on this? How do you find your edge at the edge? The first step is simple. You identify the problem or opportunity you want to take on. Second, you find a partner who can define the right mix of AI, computing, software, and networking to help you do it. And third is where the magic happens. You securely and seamlessly integrate all your apps, data, and infrastructure from edge to cloud. And when you're taking on something new, flexibility to scale is critical. You need it all available as a service, with experts on hand to guide you from proof of concept to execution, so you can adapt as your needs change and pay as you go. Through partnerships with industry leaders like NVIDIA, HPE's Intelligent Edge solutions tick all the boxes and work with your company's technology ecosystem. All right, so here's the bottom line. The edge is where data becomes insights in real time. It's empowering businesses to unearth new opportunities. And with HPE, you can define, secure, and scale your edge. So take your first step forward and find your future at the edge.
Okay, so essentially, edge computing moves the compute power to where the data is being born, which in most cases is at the edge. Because it takes too long to send the data back and forth to the data center, we need to move this compute power out to the edge. And the number of use cases for AI and edge computing, it's massive. And together with partners like NVIDIA and VMware that has spoken previously, we really have the solutions, but also the expertise and experience to help you realize all of your potential AI opportunities. And as you heard in the end here, we can also deliver this as a complete platform. And of course, that needs to be flexible and scalable, where you pay for what you use with what we call HPE GreenLake. As Jits said this in his presentation, a data scientist might know what he needs today, but probably not what he needs tomorrow. And that is why the ability to scale is so important, because it is actually in the production phase of AI projects that many fail. So this is something that we really can help you with the GreenLake offering, and being able to package the software, the hardware, and everything, and even offer it as a managed service, if that is what you're looking for. So let's look at some of the solutions that we have in our portfolio. We have several products, of course, in our HPE compute portfolio, and these are only a few of the systems that you see on this slide. And our focus today will really be on the Apollo and the Edgeline platforms. These platforms have been purpose-built for AI application, both in the data center at our core, but also at the edge, where you maybe don't have the infrastructure to accommodate the traditional rack servers, which you, of course, could use if that suits your use case. But let us first look at the Edgeline system. So this slide is really to still illustrate the true HPE Edgeline advantage, which is a purpose-built family of edge servers. And of course, if you're going to put a server out in the edge, and that could be, as we said earlier, it could be a vehicle, it could be a boat, or any type of building where you don't have the dedicated space for housing the traditional IT equipment, then of course these systems need to be ruggedized to ensure that continued operation in the even most hostile edge environments you can come and think of. And of course you need those tools to reduce deployment and management time and the associated cost with that. And this is really a big thing when you look at implementing edge computing, because many times you may be looking at multiple sites. It could be tens of sites, it could be hundreds of sites, or even thousands of sites. And of course, then you really rely on having those tools to manage all of that equipment wherever they might be placed. But still, of course, you want the flexibility to choose the options and the software that best meets your workload requirements, right? And these systems are built on an ultra-dense and short-depth chassis that provides that rack configuration flexibility that you're used to, but in a really, really small footprint. For example, one of these systems, they are the size that you could put them in a carry-on luggage that you have on your airplane, that you take on your airplane trip. So that really, I hope, give a perspective of how small these systems can be. So they are size, weight, and power optimized really to fit in both existing environments, but also these new environments out in the edge. And of course, as you expect, you have redundant cooling and power and all of that. Because, I mean, what you don't want is downtime in these remote locations, especially if it's a really critical use case of AI or some sort of analytics. So, of course, as I said, you could use traditional rack servers for edge computing if the facilities allow it, but if they don't, Edgeline is really the perfect solution for those kind of environments. And I'm not going to go through this, but the session is being recorded and you can take a print screen. But here we have the specifics of each member of the Edgeline family. And really, these are data center standard components that are packaged and optimized for the edge. And on the far left, you can see the system that I was talking about that you could fit in a carry-on suitcase on the airplane. It's the size of a US standard toolbox. Maybe that doesn't say much for us in Sweden or Europe, but it's really, really compact. So next up is the Apollo 6500 system. And this is really the workhorse for when you need to do the training of your models that you will then maybe send out to the edge and do the inference on an edge line system, for example, if that suits your use case. So the Apollo 6500, it's really the, I would say, industry-leading enterprise platform for accelerated computing. And the reason I say that, because I haven't so far seen any other manufacturer anywhere that can match our total offering when it comes to this solution. Of course, the components aren't unique in most of the cases, but this system really delivers unprecedented performance with the latest technology, of course, from partners like NVIDIA. And as I said earlier, you want the flexibility to support a wide range of CPU and GPU configurations to meet the needs for deep learning or the complex simulations or modeling that is typical for your AI workloads. And that also means that you can choose whatever operating system you want to run on these. And of course, you have the service available, from the simple break and fix to the full service care. And that is available globally, of course, like with any other system. And as I said, after the video clip, you have that GreenLake offering where we can deliver this as a true consumption-based service that could be placed anywhere where you need it. And as with any other server that are enterprise grade, you expect redundancy on all the component levels. And this is also built on our most secure x86 architecture with our silicon root of trust security measurements. And we have our, for example, InfoSight. And for those of you that don't know InfoSight, that is our tool at HPE to predict and solve issues with the system before they occur. And with that tool, we actually use ourselves machine learning to see and predict these potential issues. So it's not only like we talk about our customers going to use AI and machine learning or deep learning. We, of course, use it ourselves for our products, but also in our production when we do quality control. So this is really what you expect from a high-end system, I would say. And one of the big highlights is, of course, the NVIDIA technology with the new A100 GPU that Jits was talking about earlier. And that is offered both in the HGX form factor and the traditional PCIe form factor, depending on what kind of use case you have and how much performance you need, of course. So just to give a comparison, the HGX form factor have close to 10 times the bandwidth compared to PCIe. So it's really a huge difference when it comes to GPU to GPU communication. So if you have several, that is given to use really. And if you compare this new A100 GPU to the previous version, Jits can correct me if I'm wrong, but I think it's like up to 20 times more performance compared to the previous generation that was the V100. And of course, you have the CUDA support on this and the NVLink and NVSwitch technology for the GPUs. So in this Apollo 6500 system, we have what we call a shared chassis infrastructure to offer that maximum flexibility. You know, supporting the next generation of these GPUs from NVIDIA, if you're gonna fully populate this system, that will require a lot of power. So up to 6.5 kilowatt at the chassis level. And of course, that needs to be provided with full redundancy. And at these power levels, we expect and we see more and more of the customers to struggle with providing both power and cooling to the racks. So we are enabling something that we call power capping. And this can be done at both the server the chassis and the rack or row level. But also for this Apollo system, we have direct liquid cooling straight from our HPE factory. So fully racked and configured for you to just drop in and hook up to water in your data center. And as you can see on the picture, you have ample of storage within the system as well. And on the cooling subject, of course, you can see you have a lot of fans there to make sure that you can support those high-end CPU and GPU options. And really, with years of experience designing servers at HPE, we know that for GPU computing, you must plan for more power and more cooling for the best GPU computing experience. So we have designed this system for 500 or even 600 watt GPUs to ensure that you have that maximum performance for your workload. And this system is offered in 2 different flavors. I will not go into any details, but you have like a 1 server node with a GPU tray on top. And then you can also have 2 separate server nodes with individual GPU trays on top, but still with that common power and cooling infrastructure in the chassis. So on the cooling part, this was actually introduced not that long time ago. It was last year, I believe. And that is the direct liquid cooling directly from our factory. That is fully racked and configured, and of course, fully supported by HPE. And this is really becoming a necessity to accommodate those high-end components with maximum performance, but also to be able to fill out the racks with this kind of system, which can be very hard in terms of cooling if you're just using air. So for those that use several of these systems in a rack, they are really starting to look at direct liquid cooling systems to handle that and be able to make the most use out of the space in the data center. And these systems are built on the standard racks, 42 or 48U height, and they are self-contained and integrated in our liquid cool factory. And they come pre-filled with liquid and will easily just connect to the already existing facility water. So you don't need to do any work for secondary plumbing to be installed. And as I said, fully integrated, installed and supported by HPE. And I've so far haven't seen any other server vendor that offer this complete package. Many times when you look at the water cooling or liquid cooling in the data center, you need to go to a third party. And then, of course, means another party that will give you support and so on. So here you can get the complete package shipped to you. And of course, consumed as a service, if that is what you're looking for. So the portfolio, this was just a short overview, but we really have like different solutions all the way from the edge to the core to handle AI really, wherever that is needed. So that is everything from me. I hope maybe I ran over time a couple of minutes.
No, that was totally fine, Alexander. Thanks for the nice video and thanks for the presentation. All right, so thank you everyone for tuning in, and I would like to thank again our sponsors HPE and NVIDIA for sponsoring this event, and also I would like to thank Frank Denneman from VMware, Jits from NVIDIA, and also Alexander from HPE for the great sessions and a lot of useful information. And we would like to see you again in the next event. We already scheduled our final event in 2021. I would say it would be the final online event. It is on vmug.se. So if you go to our website, vmug.se, it has been updated. And you can also register yourself, and the event going to be on December 2nd, in the afternoon of December 2nd.